Hello again. Let's welcome our next speakers, Venko from StorPool and Peter from Quadris, which will be talking about building a DR solution with CloudStack, something which is quite new and interesting in our community. Hi, Peter. Hi, Venko.
Hi.
Hello.
So the stage is yours. As always, all of the people can ask questions in our Q&A tab, and we will ask them at the end of the talk.
Thank you.
Hello, everyone. I hope you can see my screen. Today, with Peter, we'll present projects for building a multi-data center cloud with DR capabilities using CloudStack and KVM. Enabling disaster recovery capabilities is not a trivial task, and we'll see what are the main requirements and the challenges in this project and how we solve them. So let me first introduce myself. In the last over 20 years, I had a chance to work for different type of companies in the IT industry and to work with a variety of technologies, from starting from legacy circuit switch networks, if you remember what is this, to the latest software-defined data center. Last several years at StorPool, I'm helping our customers to define and implement the best setup for their specific project and their specific needs. I'll now let Peter to tell about the project requirements of the DR cloud and the challenges that we need to solve. Peter?
Thank you, Venko. Hi, so my name is Peter Grayson. I'm the commercial director at a company based in the UK called Quadris. Quadris is a managed service provider. We've been in business since about 2008, and we currently don't have a public cloud offering, but we're well on the way to doing that. We're probably looking to go live at the end of May. We started to do a bit of research into public cloud platforms. And one of the key things we needed was a disaster recovery solution. Traditionally, Quadris has a very strong background in business continuity and a disaster recovery. We offer a warranted solution which is hosted in our data centers, which we call a disaster avoidance platform. These are hosted single tenant infrastructure solutions based on VMware, and they're active for storage, compute, network across 2 data center locations. They're primarily based on vSAN, or the enterprise version of vSAN, which is VxRail, and we've got a lot of enterprise customers on those platforms. The idea is we're launching a public cloud platform with the ambition to convince some of those customers, instead of continually investing in those single tenant platforms, to migrate over onto our public cloud, which is certainly more lucrative for us, and arguably gives them a better return on investment for their equipment. We were really struggling to find, though, a public cloud platform that would give us anything like feature parity with that solution, unless we were to go down a VMware route and do the stretched installations that we were used to doing. But it was very difficult for us to make a profit on those, just due to the cost involved with not only the VMware service provider licenses for vSphere, but also for the licenses involved for vSAN as well. So we finally decided to go with CloudStack, having reviewed OpenStack and some other providers and discounted them due to the complexity. And then we started to speak to StorPool for use as the software-defined storage provider. Initially, we were trying to set up CloudStack in 2 different data center locations with replication between the 2, and figuring out some way to import the virtual machines from the CloudStack database onto the hypervisor host at the DR site, which is where we begun a journey of trying to write an SRM, like for those of you who are familiar with Site Recovery Manager for VMware. It has some automation into it, where it'll plug into the storage system, it'll plug into the host and fail over the virtual machines from one site to another. It uses virtual machine placeholders at the second site to do that. There was no functionality in CloudStack to do that, no capability to do that within KVM. And it was a fairly stressful period whilst we were investigating that, because it became obvious we were going to be investing a significant amount of money in development, and it would have been very difficult for us to support that. Probably some extensive changes needed to CloudStack in order to do it, certainly plugins, because we didn't want to manipulate the database directly. We then begun quite a lot of discussions with Shape Blue, some consultation with them, and we discovered that if you were in a single zone and you were using multiple pods within the same zone, then the virtual machines would actually fail over from one pod to another using the built-in high availability in CloudStack. So that really piqued our interest. So we begun speaking to StorPool about the possibility of creating a stretched cluster between the two data center locations. But unfortunately, StorPool didn't have a witness-based system which would act as a tiebreaker to cut between the two data centers. So we could have ended up in a split brain scenario. However, StorPool were really flexible in the way that they would help us to develop new features, and they came to us and said they could offer a stretched-like solution where there would be a 15-minute RPO between the two data centers. But essentially everything else would be almost automated. So we'd have a very keen RTO, which got us as close as possible actually to the disaster avoidance solutions that we've been offering in the past, and therefore gave a little bit of parity when our customers were trying to compare what they had with the public cloud offering we were moving to. So that made us very pleased. And actually, when I look at this slide now and think back to when we were trying to build an SRM-like solution for our cloud, I'm actually much happier with the situation we're in now than if we were in a situation where we had actually spent several £100,000 on building that SRM-like functionality. So I'm actually very pleased with where we are at the moment. One of the other key benefits of this solution is that we can actually test the disaster recovery on a per VM basis, which was a big selling point of this, and which is something that our customers would demand. And we can fail the machines back with zero impact as well. So it's really ended up being quite a comprehensive solution. Okay, back to you, Venko.
Yeah, thanks, Peter. So the storage part is a key component of the entire solution. And for those that are new to StorPool, I'll make a very brief overview of the StorPool storage, just to have it how it fits in the entire picture. So StorPool is a scale-out block storage software that is best for building primary storage systems for high-performance clouds. Software runs on standard x86 servers, and on top of it can run on top of the most popular Linux distribution, all Red Hat clones like Rocky, Alma Linux, but also Ubuntu, Debian. And StorPool can be deployed on dedicated servers to build a storage cluster, or StorPool can run on KVM hypervisor to build a hyperconverged cloud. So no matter what's the model of deployment, separated or hyperconverged deployment, all nodes that runs StorPool software form a cluster with a fully distributed data storage and data processing and synchronous data replication across the nodes for the data protection. So this is a very brief introduction. I will not go in more details about the StorPool. And let's now see how we build together with Quadris. We build this multi-site cloud with the DR functionality. So as Peter already said, the cloud has 3 sites. One is the main site where the main workload is running. it's usually called a protected site. Then a second site, a recovery site, where the workload can be switched to. This is site B in the on this diagram, the recovery site, where the workload can be switched to in case of failure of the main site. In this specific deployment, there is a third control site, and this control site is runs only services at the control plane. So this is the Apache CloudStack management server and some other services there. But all the services running at the control site, there is no actual workload, and the components are not critical to the service availability, the components that are on the control side. So if the control side goes down, then the cluster cannot be actively managed, but this will not affect the running services. So the main site is where all the workload is, and we are protecting it with a recovery site, site B. The distance between these two main sites about 50 kilometers. They are connected with a redundant 2x10 gig connectivity. Peter will go in more details about the network setup in a few slides. The network that connects the sites and that provides the user services provide a layer 2 connectivity for the virtual machines and for the user services, and this is done through using VXLAN. This means this type of configuration allows a virtual machine to be switched from one site to another without need of network reconfiguration. So it can keep the same IP address, same gateway, and so on. So it's very important in this type of DR implementation that we have. On the control side, we have the main components on the control side are the Apache CloudStack management server that controls all the infrastructure, but also there is a set of automation scripts that actually does the DR functionality. So I'll go in more detail in the next few slides about this DR automation script. The entire infrastructure is defined in CloudStack in a single zone. So we have one zone with two pods, one pod for each site, and in each pod we have a cluster with KVM nodes. In each site, there is a separate primary storage cluster, StorPool primary storage cluster. So the two primary storage clusters that run here in the two sites can operate fully independent. So if one of the site goes down, the other cluster will continue normal operation. However, for this specific deployment, we are using one mode of operation of StorPool that is called multi-cluster mode. In this mode of operation, the two or more clusters are presented to the external world, to the clients and to the cloud management system as a single storage system with a continuous storage space, continuous namespace. Although each of the clusters can operate independently, they are controlled with a single API access point, and they are presented to the cloud management system as a single system. This mode of operation, for this mode of operation, we have a synchronous replication of the data within the cluster for data protection, but also we have asynchronous replication of data between the clusters. And this mode of operation also allows live migration of volumes and virtual machines between the sites or between the clusters. So this is important part of the entire design. So in case of plant maintenance, for example, on the main site, this architecture allows VMs to be live migrated from the main site to the recovery site, and then you can switch off, for example, KVM host to do the maintenance, and then return the VM to the main site without any downtime and without any service interruption. To allow disaster recovery, we need that all VMs, all the data of the VMs are synchronized between the sites. So we do this through a regular snapshots. So on the main site, we have a regular snapshots of all the DR protected VMs, and these snapshots are sent asynchronously to the remote site. So on the remote site, we have a recent snapshot of all the running VMs. And if the main site goes down, then we can immediately start a VM from the latest snapshot that is on the recovery side. So this is a high-level overview of the topology. So again, the summary, everything is defined in a single zone. Each site is a separate pod. There is a layer 2 connectivity that allows VMs to switch from one site to another without a need to changes in the network settings. All the user VLANs are available at both sites. Each site has independent connection to the internet. So if the internet connection of one site goes down, it does not affect the other site. And in CloudStack, there is a single, so let's get in CloudStack, there is a single primary storage, zone-wide primary storage that is accessible by all the KVM hosts in the zone. We have asynchronous replication between the storage clusters, and we have to separate storage network, again, dependent storage network. So if something goes wrong with the storage network, it will not affect the other site, and you can switch to it without affecting the services. So maybe Peter can tell more about the network implementation, the details there. Peter.
Okay. Hopefully I don't get too many questions on this. I haven't got a network architect with me, and beyond the points on this slide, I don't know an awful lot about networking, has to be said. But the network design that we're using for the CloudStack installation is very similar to the networking implementation we use for our VMware-based DR avoidance systems. It's using a VXLAN underlay fabric. It's a full leaf spine architecture, Cisco-based, Cisco 9K. As Venko said, there are two resilient links between the two data center locations, each running very low latency. Each of them is 10 gigabits, so we've got a total of 20 gigabits per second site-to-site resilient connection. We're using 50 gigabit storage bandwidth for the storage, so 2 times 25 gig, and 100 gigabits per second total bandwidth available for guest traffic. We're using any CAS gateways for high availability of the layer 3 gateways between the two sites. Essentially, the layer 3 gateways exist at both data centers all the time. So it's an instantaneous failover if we move workloads from one site to the other, or if there's a DR activated. As Venko said, all of the IP addresses stay the same, and of course they can still access the layer 3 gateways because they already exist on the switching architecture and the switching infrastructure at the DR site. And we use HSRP for the internet range failover. So we have independent internet connections at both sides of the data centers. But for the IP addresses, HSRP fails us over, so that if we are in a DR situation, or we're doing a DR rehearsal of any kind, the customer doesn't have to re-IP their external services. It just fails over automatically. Okay, thanks, Venko.
Okay, thank you. So the primary storage is a more unusual deployment and component in this architecture. So we have one primary storage cluster at each site. So we have physically two separate storage clusters. In each storage cluster, in each site, we have a synchronous replication between the storage nodes within the cluster. This is for data protection within the site. And between sites, we have asynchronous replication. So this is done on a snapshot at a snapshot level. So we have a regular, in this case, 15-minute snapshots of all the VMs and all the volumes of the VMs made at the main site, and they are asynchronously. These snapshots are asynchronously replicated to the recovery site. Or I already mentioned, the two clusters operate in a multi-cluster mode. So both clusters are presented as a single primary storage system. It provides a single API, a common namespace, so all the volumes, all the snapshots are visible. It is a zone-wide primary storage, so all the KVM hypervisors can see this primary storage and can use this primary storage system. And this architecture allows not only migration of the data, this offline asynchronous migration, but also live migration of virtual machines. So this is an important feature for the failback process. The secondary storage, Peter, I guess, can tell more about this. I'll just show on the diagram here. We have one secondary storage that can be instantly moved to the recovery zone if the recovery site, if the main site goes down. So Peter, can you tell more about the implementation?
Yep, of course. So the secondary storage with StorPool isn't as critical in CloudStack as other architectures. The secondary storage stores templates and ISOs only. It doesn't store snapshots of virtual machines with StorPool. The StorPool driver actually keeps the snapshots on the StorPool primary storage, so it's not as critical. The templates are read on first use. They're moved from the secondary storage to the primary storage, and once that's done, that's done. So we protect our secondary storage. It's based on it's hosted on a stretched vSAN cluster between the two data center locations. The control site that Venko mentioned earlier, we have a vSAN witness sitting in that control site, which acts as a tiebreaker. So if we do lose the primary site for whatever reason, the VM that is actually hosting the secondary storage automatically fails from one side of the cluster to the other side of the cluster. So we've probably got an RTO of, I'd hazard a guess of saying less than a minute. The system's all flash, and the failover is completely automatic. So it gives you a very keen RTO, and it's synchronous replication as well. So the RPO is 0. So from a secondary storage perspective, we have automatic failover of that, no problem.
Okay, thanks. So the interesting part is how this DR actually, how it works and how we implement the DR service. So the failover procedure is executed on the DR automation. It's controlled by the DR automation scripts that runs in a separate virtual machine on site C, on the control site. And the entire DR functionality and the entire DR procedure is built external to the Apache CloudStack, so it doesn't require any changes or any new features in the CloudStack. It's done only through the using CloudStack and StorPool APIs. So what is the failover procedure? If the main site, if there in an event of main site goes down, then there is a script that basically executes the listed steps. So the first step is not mandatory, but it is recommended to fence all the hosts at the main site. This is important in case the main site is still up, but we lose the connectivity to the site. So we need to make sure that in this case there are no instances of the virtual machines remain on the main site that are still working, and that can connect to online resources and do some stuff, because we will need to bring up the instances at site B, and we do not want to have 2 instances of the same virtual machine. So for this reason, the first step is to fence the host in the main site. There are different approaches for this. Either to stop the network, or the preferred one is just to restart all the KVM hosts there. So if there are any hosts remaining, there will be no any virtual machines running on it. So the next step is to mark all the virtual machines that were running on site A as stopped in the CloudStack database. This is important because this will allow us to run the same instances on site B. And then we need to switch the plugin in the CloudStack, the StorPool plugin in CloudStack that communicates with the StorPool storage. We need to switch it. We need to switch the StorPool API that this plugin uses from site A to site B. In normal operation, CloudStack is using API endpoint that is on site A here, on the cluster of site A. But since site A is down, we need to switch the Apache CloudStack to use the API endpoint of StorPool on site B. Then we need to collect the list of all the protected VMs. These are the VMs that have a DR option enabled, and that we have all their snapshots here stored on site B. So for these VMs, we need to execute fairly simple steps. So first, for each disk of the VM, we need to create a volume from the latest snapshot that is available on site B. So on site B, from the volume, we create a snapshot that still lives on site B. And then we need to update the information in CloudStack, about this volume. So the CloudStack volume will point to the newly created volume at site B. And when we update this information, this metadata, we can just tell CloudStack to start the VM on the hypervisors of on pod B. So here is an example of the 2 most important steps here. They are just executed as a simple API call. The first is an API call to StorPool API, and this is to create a volume from the snapshot. Once we have the list of the snapshots and virtual machines and the volumes that need to be created, for every snapshot, we just execute this API call that is basically volume create, and we provide the snapshot ID, and this creates a new volume. And then once we have this volume created, then we can use the CloudStack API. Here is an example with a CloudStack, with a CloudMonkey CLI. We just update the volume metadata. Here is one example. this is the volume ID in CloudStack, and this is the ID of the volume in StorPool. So this is the volume that we created at the previous step here. And once we have this updated, we just can start a virtual machine with a single API call to CloudStack. So from the CloudStack perspective, this DR functionality is completely transparent. Everything is done through external logic. There is no any modification in the CloudStack that is required to do this. So failback procedure is even simpler. Once we have recovered the main site, first we need to make sure that there are no VMs left over there. The old instances of the VMs are not running on site A. If we did the proper fencing, then there shouldn't be any VMs running there, but this is just a double check to make sure that there will be no two instances, one running on site A and one running on site B, two instances in the same VM. So then we switch back the StorPool API from site B to site A, because site A is again the main site. And then we can just run a live migration using the standard CloudStack API for VM migration. For CloudStack, this is just two pods in the same zone with a common primary storage. So this is a standard VM live migration. And we can live migrate all the VMs from site B to site A. And when we have all the VMs migrated, then we can clean up the old volumes that are left before the failover process. All the volumes on site A. So basically, for failback procedure, it is completely transparent to the user without any service interruption. And so with this implementation, we have the following features of this multi-datacentre cloud. First, we have ability for live migrations between the sites. So this is an let's say a good side effect of the entire architecture. It is, although it's not required for the DR procedure, but we have this this option to do live migration between sites. For this specific project, the sites are running in active backup mode, so there is no active workload on site B, but exactly the same architecture can be deployed for active mode. So you can have active workloads at both sites, and the two sites can protect each other. So you can do the disaster recovery in both directions. The disaster recovery procedure and the failover process is manually activated. It is automated by scripts that runs on a dedicated virtual machine, but we do not intend that it will automatically detect such an event and it will automatically start a failover procedure, because it's a really it's a highly risk operation. So if it improperly detects failure of the main site, it may start a failover process that is will have a significant impact on the user services. So that's why it needs to be activated manually. And since this is supposed to be extremely rare event, failure of the main site, it is acceptable to be manually control this process. With this design, we can get an RPO of about 15 minutes. This is the interval between the snapshots. So on the protected side, we have a snapshot that is up to 15 minutes old. The RTO depends mainly on how long it would take to manually activate the procedure. Once it's activated, the procedure is quite fast, and it can be executed for all the VMs in just a few minutes. this architecture depends on third side to control everything, but it can also be modified to work with 2 sides only. It has some additional complication in this case. So in our case, we have a third side, and we use it as a control side. It does not require any modification to the CloudStack. So this is the CloudStack that comes from the upstream without any modification. Everything is done through external scripts. 2 important features that are often overlooked is that the DR can be enabled per virtual machine. So you do not need to enable the DR functionality for all virtual machines, and you may have less resources on the protected side only for the subset of the virtual machines. And also the DR can be executed at the VM level. So you can switch only part of the virtual machines, not all the virtual machines, while if the main site is up, the other can continue to operate at the main site. It is very important because this allows to do a regular test of the DR capability. And since the failure event is really rare event, you need to regular test the capability to switch to the recovery side in case of such event, and not depend on a few years old configuration and just to hope that everything will still work as it worked at the very beginning. So this was my last slide. We have about maybe 10 minutes for questions.
Thank you, Peter. Thank you, Venko. It's good that you managed to finish earlier because we have quite a lot of questions on the Q&A. I will start with the first one. Why not go with the CloudStack management server in each site? In theory, this should enable you to maintain a usable management plane in case any one site goes down.
Peter, would
you
prefer you to answer this because, yeah.
Yeah, in theory it does. You've still got to look after the database has still got to be looked after as well. So we've got to have some sort of synchronous replication of the data center, and it just gave us synchronous replication of the database, and it just gave us some unwanted complications when we were thinking about a site failure. We've got complete independent out-of-band management for both data centers, but still we just felt more relaxed about having the third data center location for the control site with our portal as well, so that it is totally unaffected if we lost the primary site and we didn't have any complications with failing over the database. And we had a third location already, so it wasn't like we were adding any costs or anything to this system. But I think if you had 2 data center locations and you didn't have a third and you wanted to look at a different architecture, then as Venko mentioned before, it's perfectly possible to do it.
And is there a plan to deliver AC management as container?
Sorry, could you say that again? I missed that.
Do you have any plans to deliver AC management as container?
Yeah, I mean, not in phase 1, but I mean, we do containerize a lot of the solutions that we do at Quadris. We have a monitoring system that runs in containers. So yeah, it's something for the future. I mean, at the moment we're looking to launch our solution as quickly as possible to market. So we've tried to keep things as simple as possible. As I mentioned earlier, I'm pretty pleased with the solution we've got in such a short amount of time without having to go and build a whole load of automation to fail over VMs and manipulate the database and all kinds of complicated API queries. But yeah, so this is just phase 1 for us, really.
Thank you, Peter. Going to the next question. In the asynchronous replication, if you choose not to replicate a particular customer workload, is this possible? Yeah,
the replication's chosen on a per virtual machine basis. So it's controlled by tags basically. So those tags will mark it. The system that does the replication from a StorPool perspective is called volume care, and that's what controls the snapshots, the 15-minute replication. Volume care picks up the tag on the virtual machine and enables the disaster recovery for it. We also pick up that tag as part of our billing process to to charge the customer for the DR capability on the per virtual machine basis. So it is very granular configuration. The customer doesn't have to enable the entire domain for disaster recovery.
What kind of latency can the system tolerate between the sites?
Well, it's not actually synchronous. So you think about a synchronous system like a stretched vSAN, for example, or some sort of metro availability with NetApp. The it's very sensitive to cross-site latency because you've got to get write acknowledgers back before your virtual machine will continue. And so it's essential to have less than 5 millisecond round trip time. Well, because this is asynchronous, remember, write acknowledgements are sent back from the local cluster only. So latency is not a huge problem for us. We do have a good latency between the two sites. It's 10 gigabits, gigabits per second dark fiber between the two sites, and I think we've probably got something like 2 milliseconds or perhaps 3 milliseconds of round trip latency between the two sites. If you were running this thing in active mode, maybe the round trip time might become a problem, but not in the implementation that we've got. So like I say, it's not a synchronous cluster. So,
going to the next question, is the VPC VR tier network configured using VXLAN in the DCDR scenario?
It is. It's a good question. Yes, for the guest networks, we're using VXLAN in CloudStack, but it's CloudStack's implementation of VXLAN is not like a full EVPN configuration. It uses VXLAN on top of a VLAN, which confused us a little bit initially, but we've got it working. There's two VLANs, one at primary site, one at secondary site. They've actually got the same VLAN ID from a CloudStack perspective, but the stretched layer 2 connection between the two sites is handled with VXLAN on the switch side. From a VPS perspective, when you create a virtual router, if you have both pods enabled, then CloudStack will actually use both pods. So you end up in a situation where you get a virtual router deployed at your DR site, which obviously you don't want. If you then you would have some issues with cross-site latency, and obviously if you lose the one site, you've no idea where your virtual routers actually are. So our solution to that is, in normal operation, is to disable pod B, which is the DR site, and then CloudStack doesn't use it for any virtual routers or infrastructure virtual machines, system virtual machines. They all get put at pod A. Part of our failover process is then to disable pod A, enable pod B, delete the system VM so that they get automatically recreated on pod B, and then restart and repair the network, which then recreates all the virtual routers over at pod B.
It sounds like quite a good scenario for disaster recovery solution, but can you also do backups with it?
Yes, we do. Venko, I'll probably let you take that question actually.
Yep. So in this specific project on the recovery side, the storage system has two storage tiers. One is for primary storage that can handle the DR workload. And on the same storage system, we have a hard disk only storage tier that is used for backups. So with the same asynchronous replication mechanism and with the same service that does the regular snapshots for the DR, we are implementing a backup service at a volume level. So all the VMs that are subscribed to this backup service, there is a backup policy so for each VM, you can select the backup policy, and the backup policy defines the frequency, how often a backup through snapshots are created, and what is the retention policy for how long you keep the backups. And all the backups are actually stored on the backup tier of the storage cluster. And the restore process is you can just transfer the snapshot back to the primary cluster and restore the volume, or you can restore a volume and attach it to another virtual machine to extract some data from the volume, like specific files.
Thank you, Venko, for the detailed answer. Thank you, Peter, also for having you in this conference and for the nice presentation. We have a few more questions, but as we're really running out of time, I would encourage you to go to the lounge, and also the people who haven't heard the answer for their question, just go to the lounge zone, and I'm sure Peter and Venko would be happy to have a chat with you.
Right. Thank you very much.
Thank you.
Cheers.
Thank you. Reminding that StorPool is also a partner of our conference, and they have quite an interesting game. So check also the activity feed to discover what's the game. And we will be meeting you in the next session in 5 minutes.